The canonical ranking scheme for documents and text search is what's called TFIDF. Let's go over it here. It comes from an intuition that simple occurrence counts that we were using in our plain old vector space are not good for term weights. We do want to favor the repeated terms, so we like counting up how often terms occur. But we also want to give an extra bump, a little extra favor to unusual words in the document. Rare words that appear in a document and in a query suggest that that document's a really good match to the query. So a scheme to account for this is called TFIDF, or term frequency times inverse document frequency. Here's how it works. For every document D, we will compute what we're going to call its doc term rank. That's a phrase we'll use in this slide deck, but it's not standard in the literature. Doc term rank equals the number of occurrences of T in D, that's the term frequency, times the log of the total number of documents over the number of documents with this term. That is the log of 1 over the fraction of documents that have this term, right? Why the log? Well, think about what happens. It damps out the IDF so it doesn't grow too fast. And you can think about what's the IDF of a term that occurs in all of the documents. Well, then the fraction is going to be 1, right? And the log of 1 is 0. So the rank of a term that's in every single document is 0. Effectively, stop words do not affect search at all because their TF-IDF will be 0. It's as if they don't even show up. By contrast, if a term is very rare, it only occurs in one document, it will have the maximum possible value for total number of docs over number of docs with this term. And so the log seems to be doing something kind of right, and in the meantime it's kind of damping out the growth of this curve over time. So the doc term rank is the term frequency times the inverse of the document frequency with a log around it. So it's TF times log IDF really, but people just refer to it as TF-IDF. And this is what we're going to use in our vectors. So instead of using the raw counts, which would just be term frequency in the vectors, we're going to use this doc term rank, or the TF times log IDF, in our vectors. And then we'll do cosine similarity on those vectors of TF-IDF. And that model, cosine similarity over TF-IDF scores, is the standard model for ranking in text search. Now all we need to do is index that so that we can do our lookups quickly. All right, and so we're going to need a little more info in our schema to calculate IDFs, and then we're going to have to talk about how we compute TF-IDF on the fly during query processing. So in our schema, we're going to add a table called term info, okay? And for each term, it's going to count the number of documents for that term, which is the denominator of the IDF, right? And you can think of this as a query or view over the inverted file table. It's just an aggregation query, right? It's a count query per term, group by term, over the inverted file table. So you can think of this as a materialized view. And as an exercise in SQL, you should write down the SQL for that view, okay? I kind of gave it away. Meanwhile, we're going to extend our inverted file table with an additional column, the doc term rank, which is the TF-IDF corresponding to that term doc ID pair. We're going to do that for every term doc ID in our inverted file table. So we'll have that value at hand when we're doing query processing. We have an expanded schema for the documents, but we still have to compute the TF-IDF for queries as they come in. So given a query doc, like a query Berkeley database research, we can compute the doc term rank for each term quickly. So for example, for Berkeley, to compute the doc term rank, the TF is 1 because the term Berkeley appears in the query only once, and we can compute that by just examining the query. And then the log IDF of Berkeley is computed the way we always compute IDF. We look in the term info table, we find the num docs with that term, and then we take that as the denominator of the fraction total docs over num docs, and we take the log. Total docs is the total number of documents in the corpus, which is stored on the side of the index there. And we can call the resulting value Berkeley query term rank. And we can do a database term rank, query term rank, and a research query term rank. And those three things will be used in computing the actual query against our schema. So let's look at that next. In SQL again, we have our inverted file. And now we have doc term ranks in the inverted file. And we're going to create a view to make this easy to read. And that's just the Boolean query result. It's the intersection, the merge intersection of the postings lists for Berkeley database and research. And from that view, we're going to create a query that's going to fetch the doc ID, and then the ranking is going to be the vector product of the query term ranks we just computed on the previous slide for each of the query terms with the document at hand. So we're going to take the Berkeley query term rank and we're going to multiply that by the TF-IDF of Berkeley in the corpus. We're going to take the database query term rank and multiply that by the TFxIDF of database in the corpus. And we're going to take the research query term rank and multiply that by the research TFxIDF in the corpus. And the sum of those things is the dot product of the query vector and that particular document's vector. So if we order by that dot product, we'll get the values we want in descending order properly. Having written this down in SQL, we now need a query plan to evaluate that query. And one of the heuristics that we'll use right away is we'll only rank Boolean results that qualify. In other words, documents that contain Berkeley and database and research. Now this is a heuristic. There may be nearby documents in vector space that use different words. That's possible. And then you can think about, well, if you wanted to be more relaxed and not require all three of these terms, what could you do? For example, could you augment this query plan to require only pairs of terms or even only one of the terms? All right, I'll leave you to think about that offline. It's just sort of a decoration of this query plan. But in the end, we're going to merge join posting lists to form intersections, and we're going to compute vector products while we're merging. So for each doc ID that matches in the join, we'll compute the cosine distance to the query as the expression you see in the box on the upper right of the slide, the sum of products. And then we're going to feed this into a sorting algorithm that's going to sort by the vector product similarity metric. The remaining challenge for performance here is the sort box at the top of the screen. In particular, we have to face the fact that sort is a blocking operator, and it won't produce that first page of the top 10 outputs until it's sorted the entire input, and that seems a little disappointing. So we have to come up with heuristics to get around that, and the heuristics tend to be kind of specific to search engines, and we won't learn them in detail here. But the basic idea is we'll find a way to prune the input to sort. We will sort only the pruned list of things that we think are likely to be in the top 10. We'll show the top 10 of the things in the pruned set. And then in the background, perhaps we can sort the full set so that it's ready for the second, third, and fourth pages of results and so on. But that first page of results will have to be heuristically filtered from the full set of candidates.